Welcome to Let's Get to the Marks. We're looking at the A-Level Chemistry, Paper 2, Organic and Physical Chemistry. This is the 2023 paper walkthrough. Don't forget to pause the video at the start of the question and then unpause when you want to see the answers and the explanation. Really helps if you hit the like. Let's go. Okay, guys, question 1. This question is about the rates of reaction. Figure 1 shows the apparatus used to measure the rate of reaction when an acid reacts with an excess of solid sodium hydrogen carbonate. That's NaHCO3. So they've got some acid in a conical flask. We've got a balance here and weighing scales or a measuring balance there. We've got cotton wool in the top of the conical flask, and we're adding the carbonate to the acid to get a reaction. Now, when different monoprotic, that means one hydrogen, organic acids are used, the rates at which the gas escapes can be used to compare how strong the acids are. So the more gas that escapes in the shortest amount of time, we're going to get a bigger loss of mass, and that's going to tell us which acid is stronger. A timer is started when the NaHCO3 is added to the acid and the mass of the carbon dioxide gas loss is recorded at regular intervals. It's assumed that the change in the mass is due to the loss of CO2. Suggest a reason why using a conical flask instead of a beaker would give more accurate results in this experiment for 1 mark. Well, think about it. What is the cotton wool for that we often put in the top of conical flasks? Some people think it's to stop gases escaping. That is a bad error. It's not. Cotton wool is porous, has tiny holes, and those holes are thousands of times bigger than any gas molecule. So gas molecules can freely move out through the cotton wool. They may be slowed down, but they can freely move out. So what's the cotton wool for? Well, any acid that spits up and hits the cotton wool, remember, we're assuming any change in mass is due to CO2. So any acid that spits out during the reaction, we're going to think and record that as CO2 lost when that isn't the case. So it's going to affect the accuracy of our results. So that cotton wool is there to trap any acid that spits out, and therefore that mass will not be lost because, of course, the cotton wool with acid is being measured by the balance. Now, just imagine you try to do this with a beaker. For a start, you probably can't put cotton wool across the top of a beaker. And a beaker's a lot wider, so you're going to get a lot more acid lost. The shape of the conical flask, the fact that it's got those sides slanting up, means any acid that spits out might not even get to the cotton wool because it will hit the side of the flask and run back down like my crazy D-grade GCSE art drawing shows. Whereas a beaker is much more open at the top, easy for acid to be lost, almost impossible to put cotton wool across the top of the beaker without it falling in. Our conical flask, therefore, is superb. All right, let's put that answer down. Okay, so the answer to 1.1 for 1 mark. Conical flask is shaped to prevent the loss of reactants, which would affect the mass, and therefore affect our accuracy. The cotton wool can be put at the top of a conical flask. It can't be put at the top of a beaker, so we get a reduction in the loss of acid during the experiment, making it more accurate. Now let's move on to question 1.2. So let's look here. Okay, we need to use figure 2 to calculate the rate of reaction at 2 minutes. Deduce the units of your calculated rate, and this is worth 3 marks. Okay, let's get into this. I'm going to zoom in a little. So let's have a look here. 1.2. Use figure 2 to calculate the rate of reaction at 2 minutes. Deduce the units of your calculated rate. So at the bottom, we've got rate and units written, and this is worth 3 marks. So we want to go along at the bottom to where it says time, and then we want to go to 2 minutes and follow the line up to where it meets the curve. Now, because we're not dealing with a straight line, we can't just take the gradient of the straight line of the fastest bit. If we were doing the initial rate of reaction, we could take right at the start the straight bit. But here, we've got a bit of a curve going on. So what you're going to do is, first of all, mark out at 2 minutes. So you can see it's about a mass loss of 2.1. And what we want to do, and I'm not very good at this, but we want to make a straight line. That's not good enough. This is a tricky bit. You've got to make a straight line through that point that touches both the top of the graph and your y-axis. Okay, so you can see I'm struggling here on the computer. It's a little bit difficult. If you've got a ruler, a little bit easier. How do you know when it's done right? Visually, no, it's never going to be quite as accurate as I can get it here, but that's about as good as I can get on the computer, it's obviously a bit easier with your ruler because you can just alter that a lot easier. Now what we want to do is draw any triangle going across. I'm trying to make the units nice for myself, okay? I'm trying to make it nice. So we're doing a tangent to the point. Make sure it touches both the axes. Make sure the space visually around each side of that line is equal. I've not done it too well. You can see the triangular space at the bottom is a little bit smaller, but it's going to come out roughly right. So now the gradient of that little tangent I've drawn is going to be equal to the rate of reaction at exactly 2 minutes. So I'm basically doing y over x here. So going up on my y-axis, I can see I've got 10, what's that, 11, 1.1, I've got like 11 little squares, maybe 1.1 to 1.2. I'm going to call it 1.1. And then along the bottom here, we've got, let's see, 10 little squares, 21 little squares. So that's going to be 2.1 along the bottom. So I'm going to do 1.1 divided by 2.1, which is y over x, and I'm going to get 0.524. Now, in the mark scheme, they allow you anywhere between sort of 0.45 and 0.55, something like that. I'm not really sure, but it's roughly in the right area. So we slap that down as the answer, and now we just need to work out the units. Well, we look at y and it's grams, we look at x and it's minutes, so it's grams per minute. Now GCSE, you can put the diagonal line, grams per minute, but at A level you need to put G to the min to the minus 1. Okay, so 1.1 over 2.1, 0.524, and that's grams per minute. Awesome. Let's move on to 1.3 and see what they're going to ask us there. Sketch on figure 2 the curve you'd expect when 25 centimeter cubed of a 2.23 mole per decimeter solution of chloroethanoic acid reacts with an excess of sodium hydrogen carbonate. Suggests why chloroethanoic acid is a stronger acid than ethanoic acid. So we've got 3 parts to this question. We need to start with a sketch and then finish with a suggestion and a written answer. Okay, let's get into it. Okay, let's do this. 3 marks. So something to notice here, checking out the graph. Figure 2 shows the results of this experiment when 25 centimeter cubed of 2.23 mole of ethanoic acid reacts with an excess of sodium hydrogen carbonate. So what we can tell from this is that actually the moles are equal. So because N over CV, right, the concentration and the volume are equal for both the chloroethanoic acid and just the ethanoic acid, which means we've got the identical amount of moles of both acids. So we're told the chloroethanoic acid is stronger, which means it's going to dissociate more fully, releasing hydrogen ions faster. So it should react faster, the chloroethanoic acid. But the fact that they have an equal amount of moles means that the total amount of carbon dioxide that can be released should be roughly the same. So what I need to show on this graph is a faster rate of reaction but ending at the same mass of CO2 released, i.e. the same amount of product, because we've only got the same moles of reactant. So let's show that on this graph. And so your 2 marks are going to be for drawing a line that's steeper and to the left, so showing that it's releasing CO2 in a shorter amount of time, although it shouldn't go above that line. That would be bad. I keep going above the line. I'm so rubbish at drawing hands-free on this thing. Right, so it's got to come up here and then finish to show the same amount of CO2 released. There we go. All right, and that will get you both marks. So a steeper line to the left, finishing in the same place as the other acid. Now for the final mark, we really want to look at why is chloroethanoic acid stronger than ethanoic acid? Well, what's the only difference? Well, chloroethanoic acid has a chlorine atom. So here's ethanoic acid. See, it's got the OH bond, and it's really about this OH bond over here. How easy is that to break? Well, obviously the electrons are pulled slightly towards those oxygens because they're electronegative, but guess what? Chloroethanoic acid has a chlorine atom, which is also electronegative and electron withdrawing. So the electron cloud across the OH bond is going to be drawn towards that chlorine atom. This is going to further polarize the bond, increase the delta positive on the hydrogen, and therefore weaken the OH bond, the oxygen hydrogen bond, or hydroxide bond, the alcohol bond, whatever you want to say. So it's more strongly polarized, weakening the bond, easier to break. Therefore, it's going to dissociate more fully, releasing those hydrogen ions and reacting faster as an acid. So chloroethanoic acid is going to be a stronger acid, as that bond is more easy to break. It's going to dissociate faster than ethanoic acid. And here we go. A and B react together in the presence of an acid catalyst. A aqueous, 2B aqueous goes to C aqueous, D aqueous. The rate equation for the reaction is rate equals K, B to the power of 2, hydrogen ion concentration. So table 1 shows how the values of the relative initial rate vary with the different concentrations of each reagent at the same temperature. Complete the table by calculating the missing values for 3 marks. So we've got experiment 1, 2, 3, 4, and along the top here we've got the different reactants. So we've got A, B, and hydrogen ions. We've also got the relative initial rate at the end. Okay, and we can see there's some gaps there. So our first thing to fill out is in experiment 2. You can see we need to fill out the relative initial rate. So what do we need to do? Well, we need to look at the rate equation and see what has changed. So the relative initial rate was 1. Now we can see that B and H have stayed the same. As you would do in these experiments, you only change one reactant at a time, and the reactant they've changed is A. It's gone from 0.4 mole per decimeter to 0.5 mole per decimeter. But notice that A does not appear in the rate equation. And that the rule tells us if a reactant doesn't appear in the rate equation, we can see there's no A in the rate equation, it doesn't affect the rate of reaction. And so as B and H, which do appear in the rate equation, haven't changed, the relative initial rate is going to be identical. It's still going to be 1. So the rate is 1. They've changed A, but it has no effect on rate. Now let's look at experiment 3. We can see A is 0.4, H hasn't changed, but the rate has changed, which tells me that B must have changed. B appears in the rate equation. So we need to find out what B is. How are we going to find out what B is? So the first step into finding out the concentration of B is we're going to need to solve the rate equation to find K, because we can't find B without K. So let's rearrange the rate equation to find what K is. So here's the rearrangement. We're going to take rate, divide it by B to the power of 2, or B squared, times the hydrogen ion concentration, and that will give us K. So we know that the rate is 1 for experiment 3. We know that for experiment 1, we're doing this to find K, so we want to either use experiment 1 or experiment 2. So we're going to do 1 over 0.20 squared multiplied by 0.10. And we use experiment 1 or 2 to find K because we have all the data. And so we can see that K is going to be 250. So K is 250. Now, we've found K, but we still can't fill it out. We can now rearrange the equation a second time to make B the subject. And from that, we can use our 250 for K and our 0.64, 0.1, and 0.4, all the other data we have, to work out what B is. So rearrange the rate equation to find B. We're going to do rate this time over K times the hydrogen ion concentration, and that is going to give us B squared. However, we want to square root both sides to get rid of the square, and then we'll find B. So we want the square root of the rate of K over K times H. We know that the rate for experiment 3 is 0.64, so the rate's gone down. We know that K is 250 for all of these, so we're going to do 250 times 0.1, which is the concentration of H, and that is going to give us B if we square root it. So let's whack that in the calculator and work that out. 0.64 over 250 times 0.1 square root. Make sure you use brackets in all of this as you won't get the right answer. B is equal to 0.16. Boom! We picked up our second mark. Awesome. So, hope you're liking the video. Take the time now to quickly hit the like button. It helps my channel massively and helps me make a video. I'm trying to make a video every single day at the moment. All right, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving on.
Finally, just plonk the data. This is for the final question in experiment 4 to find the relative initial rate. It's the easiest one of the lot because we're just using the rate equation in its pure form. Rate equals K multiplied by B squared times H. So just plonk that data in and let's see what we get. So we're going to do 250 times 0.3 squared, or 0.30 squared, same thing, times 0.06. And 250 times 0.30 squared times 0.6 is going to give you an answer of 1.35, and that is the relative initial rate, and that is going to score you all 3 marks. So 1 for getting the 1.00, 1 for the 0.16, and 1 for the 1.35. Don't forget to smash the like, share, subscribe. Let's move on to the final part of the question. Okay, for 2.2, a suggested mechanism for the reaction is shown. Step 1, B plus H goes to BH. Step 2, BH plus B goes to B2H. Or step 3, B2H plus A goes to C plus D. Deduce the rate determining step for this reaction. That's the slowest step in the reaction, the rate determining step, the one that limits the rate of the reaction. So it's the one that takes the longest. Give a reason for your answer. Well, you need to know this rule off by heart, and that's that all the reactants in the rate equation must appear in the rate determining step, and they must appear in the same amounts by the end of that step as they do in the equation. So if you can remember the equation from above, we should be looking for the reactants that are in the rate equation. Now, they can be derivatives of the reactants. So it could be like B2H2 would be fine. So it can be something that contains those. All right, let's have a little whip up to that rate equation. If you can look at this rate equation, it's K and B2H. So there should only be B and H in the rate equation, which means step 3, step 3's got A, C, and D. They don't appear in the rate equation, so they're not our rate determining step. Okay. We would look at step 1 and 2 and say these look like they're going to be the rate determining step, and the actual answer is step 2. Why? Because if we look at the rate equation, that it was B squared, or B, 2 lots of B and 1 lot of H, and that's the same amounts that we see here in step 2. Step 1 doesn't have the correct amounts. It has the correct elements, ions, reactants, but not in the right amounts to appear as the rate determining step. God, I'm waffling. For A-level chemistry for AQA, let's get into it. This question is about intermediates in reaction mechanisms. 3.1, figure 1 shows an intermediate formed in the first step of a nucleophilic addition elimination mechanism. Complete figure 3 to show the structures of the 2 reactant species with curly arrows, relevant lone pairs of electrons involved in the formation of the intermediate shown on the page. Draw curly arrows, relevant lone pairs on the intermediate to show the final products and how they're formed. 2 marks for each of those sections. Pause the video, have a go. Okay, going through the walkthrough. So first of all, I want to split this up and work out what the reactants are. So we can see there's a chlorine atom attached here. So this is an acyl chloride. It looks like propanoyl chloride. That's what this was originally. How do we know that? We've got that single bond to the oxygen with a minus, so that's formed by the breakdown of the carbonyl bond, the COO, and that leaves us with methanol over here. Now, how does methanol attack an acyl chloride? Well, an acyl chloride has a delta positive carbon atom. Because of the polar carbon chlorine bond and the carbonyl bond draw electrons away from that carbon atom. Okay, now a carbon atom cannot have 5 bonds. So if this methanol is going to attach from its lone pair to the delta positive carbon, one of the carbonyl bonds in the oxygen, the double bond in the oxygen, is going to have to break. So these are our two curly arrows and our first two marks with the reactants and curly arrows to show the intermediate. We now need to add lone pairs and curly arrows on the intermediate to show what happens. Well, we're now on to the elimination phase of the nucleophilic addition elimination. So we've got addition in the what I've written in the green. We're now going to look at elimination. So first of all, again, this oxygen has three bonds around it. Oxygen can't have three bonds around it. That's why it's got that plus sign on it. It's like an oxonium ion or something. And so we're going to draw a pair of a curly arrow to show a pair of electrons going from the HO bond to the O. That's going to get rid of that positive charge on the O. And we're also going to have to get rid of the chlorine. And this means that we're going to have a hydrogen ion, a positive hydrogen ion and a negative chlorine ion with a lone pair that are free. Now, this isn't part of the question. This is just to show your understanding. Normally, when we have reactions involving acyl chlorides, we get hydrogen chloride as a product because the chlorine atom normally breaks off in acyl chlorides when they react. So what's going to happen is this carbonyl bond is going to reform. So the lone pair from the oxygen, you have to draw two dots on the oxygen to show the lone pair is going to go back to the single bond to reform the double bond there. And the methanol is going to break off. Sorry, the hydrogen from the methanol is going to break off. And there we go. We're going to be left with an ester. And that's the other two marks for those three curly arrows and lone pair. Okay, let's move on to the next part of the question. So we're on to 3.2. Figure 4 shows an intermediate formed in the first step of a reaction mechanism of methylbenzene. So we've got methylbenzene here. We've got the intermediate again shown on the right. Complete figure 4 to show the reactant species and any curly arrows involved in the formation of the intermediate. So we need the reactants beforehand. Draw a curly arrow on the intermediate to show how the product is formed. So we need to add a curly arrow to the intermediate and give the name of the reaction mechanism 4 marks again. Pause the video, have a go. Okay, well, one of our reactants is going to be methylbenzene. This is kind of testing you on your knowledge of the nitration of benzene. See, benzene rings have 6 hydrogen atoms, and this one would have 5. But we've got the NO2, the nitronium ion, and this is going to attack here. So do remember that the curly arrow has to come from the benzene ring, the electrons to the positive. We always go from electrons to positive, never positive. You never draw a curly arrow from the positive. Protons are locked in the nucleus, they can't move. Of course, that means we have broken the delocalized ring, so it needs to reform to stabilize itself. So the hydrogen on the intermediate, its bond donates its pair of electrons back to the horseshoe to reform that delocalized ring. And so we're going to get 2 marks for showing the nucleophile, the NO2 plus ion, and showing the curly arrow from the ring either to the nitrogen atom or to the positive sign. And then we're going to get 1 mark for showing the curly arrow in the substitution. Sorry, that's an electrophile. I called it a nucleophile. Electrophile because it's attracted to electron-rich or dense areas. So, and now we just need to name it, and it's electrophilic substitution because you're swapping the electrophile for the hydrogen atom on the methylbenzene. Okay, let's move on. 3.3, figure 5 shows the reactant species involved in the first step of a mechanism. So we've got propanone, that looks like. We've got a carbonyl group on a skeletal formula. We've got a hydride ion. Complete figure 5 to show the structure of the intermediate formed with curly arrows involved in its formation. Give the name of the reaction mechanism. That's going to be a mark as well. And again, it's 4 marks. So this is propanone we're dealing with. Pause the video, have a go, obviously. And that's a ketone. Now, you need to know your reactions of ketones, and we can reduce aldehydes and ketones. It's part of your carbonyl compounds content, and this is a hydride ion. Okay, so it's a hydrogen atom that's negative. We always know hydrogen ions are normally positive. This is a negative hydrogen ion. Okay, it's got a lone pair of electrons, and here I'm drawing the displayed formula. And you know there's going to be a delta positive on that carbon because of the oxygen drawing electrons away from it. So it's always going to be under attack. This is a nucleophile this time because we've got a lone pair of electrons attracted to the positive charge. So it's seeking positive charge, that nucleophile. with that lone pair. Always draw the curly arrow from the lone pair to the region of positive charge. And that means we're going to have 5 bonds around that carbon atom. We can't have 5 bonds around it. So as you can see, we're breaking down the carbonyl bond temporarily. That is going to break down and form our product, which is going to have a very similar structure, except for we've got that lone pair of electrons on the oxygen because the carbonyl compound broke down, and the minus sign. And that's going to get you a mark for showing the intermediate. Of course, what's going to happen later on, if you're wondering what the hell is this reaction, this is reducing the ketone back to a secondary alcohol. And you've got a hydride ion, but you're going to have another hydrogen. You require 2 hydrogen ions to reduce this. You can have another hydrogen ion, a positive one, that will attach to that negative oxygen, forming an OH group. And so it's going to go from propanone to propan-2-ol, which is a secondary alcohol. And this is known as nucleophilic addition, this reaction. And it isn't part of the question, but you use sodium borohydride. It's got other names, but NaBH4, that's normally your reducing agent. We normally just show hydrogen ions. So you can see we start off with a negative hydrogen ion attacking the carbonyl, or the delta positive carbon atom. And then we get a hydrogen ion, which is positive, which normally comes from water. You normally have water dissolved in methanol when you reduce ketones back to alcohols. And sometimes we get the hydrogen ions from a dilute acid. But that was just some additional information if you were interested. All right, guys, I hope that video helps. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Let's go. Acrylonitrile can be used as a starting material for the synthesis of butane 1,4-diamine, as shown in this reaction scheme. So you've got reaction 1 involving hydrogen bromide going to isomer W, which seems to have a nitrile and a bromine atom on. We've got reaction 2, which has a nitrile on each end, and then reaction 3, which ends up with an amine on each end of the molecule. So the first question, 4.1, is use IUPAC rules to name isomer W. Okay, so for 4.1, first of all, it's got 3 carbon atoms, so it's going to be propane. You start with the main chain. How long is it? Then have a look. You've got a nitrile. Why have I put that as carbon 1? Well, because nitrile groups, things like carbon dioxide, carboxylic acids, aldehydes, nitriles, they always have to be carbon 1 because they can't fit on any other carbon. They'd have too many bonds. So we know it's going to be called propane nitrile. Now we just need to check out this bromine atom and see which number of carbon it's on, and it's on the 3rd, so it's going to be 3-broma propane nitrile. We could call it 3-broma propan -1 nitrile. Okay, 4.2, reaction 1 produces a mixture of W and 2 other isomers. Draw the structure of the 2 other isomers, explained by considering the mechanism of this reaction, why all 3 isomers are formed. So first up, going to draw out our starting molecule, which was propan nitrile. Okay, so you can see here 3 carbons, we got a double bond there. And so we have HBr, which the hydrogen is going to be delta positive. In AQA, they're not so big on you showing this, and the bromine is delta negative. It's been polarized because the bromine is more electronegative than the hydrogen. What happens is a pair of electrons from the double bond will leave the double bond and go to a hydrogen, but the hydrogen has options. It could form on either of these 2 carbon atoms. Now, the bromine hydrogen bond will also break, as hydrogen can only form 1 bond. It's basically like a group 1 element. And so a pair of electrons will go to the bromine, leaving us with a bromine ion, but we'll come on to that later. So what I'm going to do now is I'm going to go through the 2 different possible products here. This is a 6 marker, so we need to explain it all, that can form. And this is the intermediate that forms when the hydrogen from the hydrogen bromide joins on. And this is the intermediate which is created in the formation of the minor product. And the minor product is going to be 3-broma propan nitrile, the one we drew above. That's the minor product. So this carbocation, where you see the positive charge on the first carbon, is a less stable formation. This molecule is the carbocation, and the positive carbon is the one there the third carbon there. So this is a less stable formation because it doesn't have any alkyl groups. Now, when you're thinking of alkyl groups, you're thinking of methyl and generally ethyl groups, side groups. What these side groups do is they donate electrons to stabilize the carbocation. Those electrons are sort of donated, or an electron cloud moves towards that positive carbon atom and stabilizes it. So it's much more likely to form if you have alkyl groups attached to the carbocation. Remember, the carbocation is the description of the whole molecule with the positive charge. Lovely jubbly. So what we want to do here, I'm just drawing that in red just to show you the hydrogen has already attached there. Now let's do the second, the major product. This is the one more likely to form. And it's more likely to form because the intermediate carbocation that is formed before the bromine joins on, the intermediate has more alkyl groups attached. And you see here we've got a CH3. That CH3 is a methyl group. And that methyl group is electron donating or electron feeding. It donates its electrons towards that positive carbon atom on the carbocation, and it stabilizes the carbocation, making it more survivable, more stable. Okay, so it means it's much more likely to form. And that means that you're much more likely, because when the bromine ion attaches, you're going to get 2 bromopropionitrile. And this is going to be much more common because the carbocation, this carbocation, is the more likely one to form. So you're much more likely to get 2 bromopropionitrile than you are 3 bromopropionitrile. The bromine atom equally likes these. It's just attracted to the positive carbon. It equally likes these. But what we're saying is that the first carbocation, the one on the left of the screen, is much more likely to form. So if 90% of the carbocations that form in the intermediate phase are on the left, you're going to get a lot more of those 2 bromopropionitrile. Okay, so this is going to get you a whole bunch of marks because what we've got here are 2 isomers of W. Okay, really the minor product is the one above, is W, and then we got this other version of W where the carbocation is different and more stable, and so you get 2 bromopropionitrile. So we've got 3 bromopropionitrile and 2 bromopropionitrile. They're 2 of the 3 isomers. So where does the third isomer come from? So we're looking at where does the third isomer come from. The minor product on the right here is the one above. That is W. That is 3 bromopropionitrile. This second one here, the major product formed, is going to be 2 bromopropionitrile. So where does the third isomer come from? Well, it all is all to do with the 2 bromopropionitrile. If you look at the 3 bromopropionitrile, can you find a chiral carbon? And you can't, because all of the carbons don't have 4 different groups attached, whereas the 2 bromopropionitrile has a chiral carbon, the one I've put a star by there with the bromine, the nitrile, a hydrogen and a methyl attached. And if you have a chiral carbon, 4 different groups around a carbon atom, then you can make non-superimposable mirror images, otherwise known as optical isomers or enantiomers. So totally up to you what you call them, but they're going to be looking for that keyword in the mark scheme. And that means that 2 bromopropionitrile then has 2 optical isomers of itself here. So this is where we get our other isomer. And basically it's going to form sort of a tetrahedral structure. And you just need to put the CH3 at the top, straight line to the H, and the Br and the Cn, one going in and out. Now you can choose any ones to do this with, as long as you can use any groups in any position, as long as your 2 are mirror images of each other. So you can see here, the only difference when redrawing this is everything is swapped around. And there we go. That's going to get you all of the marks for showing the enantiomers and explaining why they form, because we have the chiral carbon on 2 bromopropionitrile. And so that is why we end up with 3 different versions. Okay, let's move on to the next question. So for 4.3, you can see they've repeated the reaction scheme here. They've got the whole reaction scheme repeated. And 4.3 says identify the reagent that is warmed with isomer W in reaction 2. So looking at reaction 2, we're going from the 3-bromopropionitrile, and we're going to a molecule with a nitrile group on each end. So what's happened? Well, a nitrile has been substituted for that bromine. It's like a nucleophilic substitution. So the nitrile has been substituted there. Now, what is a source that you know of nitrile ions? What's our source? What would we use as a reagent to get some nitrile ions? Because you can't just get a beaker with or a bottle of nitrile ions. So you would need potassium cyanide or hydrogen cyanide. We'd actually use potassium cyanide here. Hydrogen cyanide's a little bit dangerous. Or sodium cyanide we could use. And we need them dissolved in ethanol. And there we go. Those are our reagent and our conditions. Now look at the next question. State the reagent and the reaction conditions for reaction 3. So we're going from these two nitrile groups, one at each end. What's really happening? Have a look at the diamine below. So you can see we've got a diamine below. Look what's really happened. It's got the same number of carbons. There's 4 carbons, but it's had hydrogens added. And in fact, it's got 4 CH2s. So it means that the 2 carbons with the nitriles must have 2 hydrogens added to them. And then it's telling us that the nitrogen atoms have got 2 hydrogens on them. So actually, what's been added in this addition reaction? Well, we've added 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Atoms have been added, or 4 hydrogen molecules. So the reagent we need for this is hydrogen, and you use a nickel or platinum catalyst. We use this in the hydrogenation of alkenes as well, to make alkanes. So you probably remember that one. Okay, now for the reaction, it's dead easy. We just got to copy out the original formulas and then just balance it. They just want you to basically acknowledge that there's 4 hydrogen molecules. The rest is just copying it out, the reactant and the product, whacking on the 4 hydrogens that you need. And if you count again, you've got 2 hydrogens on each amine and 4 times 2 on the CH2 in the product. That makes 12 hydrogens. And then if you go to the reactant, you've only got 4 hydrogens, 2 CH2s. So you're going to need another 8 so that you have 12 hydrogens on each side. And there we go. That's how you get your 2 marks. Right, let's zing to 4.5. So for this question, they want us to work out what X and Y is. So how much X is there and how much Y? We're dealing with butane 1,4-diamine and hexane dioic acid. There's 5 of each of them, and they're saying, what is X? So how many molecules would you get if you combined 5 of the left one of the butane 1,4-diamine and the hexane dioic acid? I'm going to use A and B. So if you have 5 of A and you have 5 of B, you can only make 5AB. So the answer to X is 5. And then when we look at Y, what is Y? Y is a molecule of water, and that comes off in a condensation reaction when any of these molecules or any of these polymerizations happen. So all I need to do is add 5 A's and B's and all the bonds and then count how many water molecules have come off. So let me just count out 5 A's. The A's stand for butane 1,4-diamine and the B's hexane dioic acid. They're the 2 reactants. We've got 5 of each. So just to make sure I've got 5 A's. Yes, I've got 5 A's. I've got 5 B's. So 1 water molecule is going to come off in the formation of each of these bonds. I'm not going to draw them all out. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to get 9 water molecules come off in that situation. So there you go, 2 marks. Boom. Let's move on to the last part of the question. It's 4.6. So figure 6 shows a section of the nylon 4,6 polymer molecule. Draw on figure 6 another section of the nylon 4,6 polymer showing 2 hydrogen bonds between the sections. All you need to do is copy on either the left or the right. I'm going to do it on the left here. You could do it on the right where I put that arrow. Just copy out the same molecule again. You could reverse it, turn it upside down if you want to suit your purposes. Now, I'm just going to copy it out again. I'm a bit sloppy at this on the computer, but there we go. So just make sure that you get it all exactly right, and then just show how hydrogen bonds would form between 2 layers or 2 strands of this polymer. So my oxygen has a lone pair, and that is going to be attracted to the delta positive hydrogen atoms. You don't need to show the delta sign in AQA. And so we're going to get a dashed line. Don't do a straight line because that would be a covalent bond. We can use a dashed line to indicate the intermolecular force we call hydrogen bonds. And it's between oxygen and hydrogen here. So there we go. I could have had the amine groups attaching to those carboxylic groups on the right. All right, guys, welcome to Let's Get to the Marks. We're looking at an NMR question. So question 5, this question's about compound Z with a molecular formula C7H12O3. Figure 7 shows the infrared spectrum of Z. Okay, we've got transmittance on the left here, and we have wave number at the bottom. Identify the bond that causes the absorption at 1725. Once again, always pause the video, have a go before looking up and watching the walkthrough. All right, there we go. So that's the wave they're talking about. This one at 1725. All we have to do here is flip to our data sheet over here, and we need to make sure we're looking at the right one. And it was asking us about infrared. So we check this out and we go 1725. You can see there 1725 falls between these two numbers, these wave numbers. And so the bond we're looking at is the carbonyl bond. Awesome. So let's zing back there and put our answer in. So the answer here, we're looking at the carbonyl bond. And hopefully that's a nice, easy starter for this question. All right, let's zing down to the next part of the question. So figure 8 shows the C13 NMR spectrum of Z. Here's figure 8. You can see all these lines here. We've got chemical shift in ppm along the bottom. How many different carbon environments are there in a molecule of Z? So once again, pause, have a go, and I'll explain. Okay, so the way to do this, the number of different carbon environments shown by the C13 NMR is the number of peaks. So count the number of peaks. We got 1, we got 2, we got 3, we got 4. Now here's a tricky bit. You got 5, you got 6, and you got 7. Now this might give people some confusion. Okay, the answer is actually 7, as you can see there, and that might seem obvious, but a lot of people might get this mixed up with their Proton NMR or H1 NMR. Now in C13 NMR, you don't get splitting patterns. So you don't want to start thinking, oh, that's a doublet or whatever. That's not a splitting pattern. They're just two peaks very close together in the chemical shift. Okay, so it's 7 peaks. All you really get from C13 NMR, all you can really work out is the number of different carbon environments, which is shown by the number of peaks. And then you can also use the chemical shift to give you an idea of the groups. Let's move on to 5.3. So I'm going to zing down a little bit here. And we can see here for 5.3, it says state the type of carbon environment that causes the peak at 174 ppm. So we're going to go along here and find 174. It's got to be this one here, right? It's the only one in that region. And we need to use table C in the data booklet to answer the question. So we need to swing over to the data booklet, and table C is here. And we need to go down the C13 NMR chemical shift data and find 174. And you can see here, it looks like it's going to be an ester. So zinging back here, it's going to be an ester. So the type of carbon environment that shows this is an ester. So you're really looking at, yeah, something like that. You've got that environment. All right, let's zing on and stop the waffle. So let's go to 5.4 in this question. Table 2 shows the data from the H1 NMR spectrum for compound Z. So this question is testing you on your infrared, just for a mark, a couple of marks on CNMR, and then we're moving on to proton or H1 or 1H NMR. So we've been given chemical shift data here, which can help us identify the group responsible, integration ratio, which I'll talk about in a second, and the splitting pattern. So we get that extra splitting pattern and integration ratio that we don't normally get with C NMR. Explain what can be deduced from the splitting patterns and the chemical shift values for the peaks at 410 and at 126. So we're looking for our peaks at 410 and 126 and what can be deduced from that. It then says Deduce the part of the structure Z that causes these peaks 410 and 126. So that's going to be the fifth mark. 2 marks for explaining 410 and 126, and then one extra mark for putting them together to make the structure that causes those two peaks. It says use table B in the data booklet to help you answer this question. So let's tackle it, right? So straight off, I'm going to look at 410 first. It's the first one that hits the eye. So chemical shift at 410. Let's go check out what that could possibly be. So we're going to come down here. This is table B. Let's go down to 410. We can see 3.7 to 4.1 or 3.1 to 4.2. So these are my two possibilities for the chemical shift at 410. It could either be this hydrogen atom, which has got a halo attached or a halogen attached, or it could be this hydrogen atom, which has an ester link. Now, bearing in mind that we just identified there was an ester link, we're probably going to be the ester link. And bearing in mind that we also know from the stem of the question right at the very start, they told us the formula was C7, what was it, H12, and it was O3. That was the formula they gave us right in 5.1 at the start. So there's no chlorine atom or bromine atom. There's no halogen there. So we definitely know that the group or environment responsible for the 410 chemical shift is this one here. All right, let's go back, put that on our answer, and then we'll check the rest of it out. Okay, so we want to say there's a ester link at, whoopsie, 410 from chemical shift. What I can also tell from the data here at 410, the integration ratio is 2. So I'm expecting integration ratio is 2. So 2 hydrogens in this environment. It's not always 2. Sometimes it's a ratio, but in this situation, as it normally does, it's telling us there's 2 hydrogens in this environment. So we know there's the ester link from 410. We know the integration ratio tells us there are 2 hydrogens in this environment. Now we've got a splitting pattern, which is a quartet. So the splitting pattern, I can't fit it all in. So quartet tells us adjacent carbon has 3 H's attached. So straight away, what we're looking at is it's telling us that the neighboring carbon next to the hydrogen of this one has got 3 hydrogens attached. So what I'm kind of thinking here, folks, is we got this ester link, okay, like so, and then we've got CH2. Why do I know it's CH2? That's because the integration ratio was 2. So this hydrogen here, it could be the one below, the one underneath, it could be either hydrogen, is giving me the 410 chemical shift because it's saying it's attached to an ester link. And also that we have a quartet here, and that is telling me that it's adjacent to a carbon, the carbon attached to this hydrogen, is adjacent to a carbon with 3 hydrogens attached. Quartet is 9 times out of 10 telling you there's a methyl group attached. So really, that is what 410 is telling us. Okay, back from the mini break. Let's go. Where were we? So what we're saying here is that this hydrogen, the fact that this hydrogen has an integration trace of 2 tells me there's 2 hydrogens. The fact that it has a quartet tells me that the adjacent carbon atom, to the carbon that this hydrogen's attached to has 3 hydrogens. Now, normally a quartet is normally a CH3 group. Now let's look at the 126. So if we look at the 126, and we can just pick any of these hydrogens, any of the 3, and say it's 126, we can see, why am I assuming this is the 126? Well, it has an I trace, integration trace of 3, telling me that there's 3 hydrogens, and it also says that it produces a splitting pattern, okay? That is a triplet. Now, what does the triplet tell you? With splitting patterns, they call it the N+1 rule. I like to think of it as the N-1 rule. So you take the triplet, and if you take away one from that, you get two, and that tells you the amount of hydrogens next door. But most of the books call it the N+1 rule, and they say um, the splitting pattern is one more than the number of hydrogens on the adjacent carbon. So if you get a triplet, it tells you there's a CH2 next door. Okay. Or there's two hydrogens attached to the carbon next door. So all of that information is there. So we're going to put that down here, and we're going to say from this, we're going to say that we have the integration value or trace or ratio is 3. So 3 H's in this environment. We also want to say, I can't fit all this junk in. Splitting pattern triplet tells us adjacent or neighboring, if you prefer that word, carbon environment has 2 H's. So it makes perfectly sense that we have an ethyl group here, a CH3 and a CH2. And judging from the shift at 410, we could tell that it was an ester link. So for the final part, it says what bit of the structure is responsible for this. And essentially, we've got that going on. So we've got this is structure. That is the part of structure Z that gives us the 410 and the 1.26. So that will get you 5 marks. You're going to get 2 marks for the information. So even if you find it really impossible to do what I've done here and put the structure together, and you find that really, really hard, you can still get 4 out of 5 marks just by interpreting the integration trace and the splitting pattern. Just by saying, oh, well, look, it's got a 2 on the integration ratio. That tells me there is 2 hydrogen atoms in the environment, and the splitting pattern's a quartet. It tells me that the environment next door, the carbon atom next to the carbon with these 2 hydrogens on, has 3 hydrogens attached because it's a quartet. So, excuse me, just explaining the integration ratio and splitting pattern will get you most of the marks, even if you can't do this bit. Excuse me. So now what we're going to do, we're going to move on, and we're going to flick down. 5.5, deduce the part of the structure of Z that causes the peak at 219. Well, let's check out 219. We've got to deduce the structure that causes the peak at 219. So if we look at 219 and we go to our chemical shift, let's check that out, check that out, check that out. So 219, we're going to find that, bada bada bing, bada bong, right here, look, 2.1 to 2.6. I'm on the H1 NMR. We're going to find, again, I've got a carbonyl group, and this is the hydrogen that is telling me there's a carbonyl group there. So that's the hydrogen responsible for this pattern. And we're looking at a carbonyl attached. So let's zing back and put this piece together. So what were we doing? We were looking at 219. It's telling us that we have this hydrogen here, which is giving us a 219 parts per million, or whatever that ppm chemical shift is. And it was telling us that there is a carbonyl group attached. So that is the structure responsible. However, we've also got some other information. We have an integration trace or ratio. I keep calling it trace. It's not a trace. That's a line on a graph. Sorry about that. Keep referring it to that as blah, blah, integration trace. This is an integration value or ratio, and of 3 tells us 3 H's, okay, in this environment. Now, what some of you may get confused with is you might go, oh, but doesn't the integration trace tell you about the amount of hydrogens next door? No, it tells you about the amount of hydrogens on the immediate carbon atom. So it's telling me that there are 3 hydrogens directly attached to this carbon atom here. And actually, it's the splitting pattern, the singlet, that tells me about the next door. So singlet gives you the information about So the singlet is telling me about the carbon next door. This is the next door neighboring carbon. And what a singlet tells you is there are no hydrogens attached. So that makes sense, right? There's no hydrogens attached on this on this carbonyl group. So it does perfectly all fit together. And that is the part of the structure for 5.5. So that is your answer for 5.5. Boom. All right, we're going to move on, and I'm sure they're going to ask us to piece the whole thing together, which is always a bit difficult to do when you're on the old computer screen, but we shall give it a good go. Right, figure 9 shows the H1 NMR spectrum of compound Z. Okay, so we've got some splitting patterns. We've got the chemical shift. Suggests why it would be difficult to determine the structure of Z using the spectrum in figure 9 without the information in table 2 on page 13. So they're saying if we just had this, could we work out the structure? It would be difficult without table 2. What have we got that's extra in table 2? We've got this, the integration ratio. That graph only gives us the chemical shift and the splitting pattern. It doesn't give us the integration ratio or value or ratio, whatever. So what we want to say here is this does not have integration ratio. So it's going to be hard because this doesn't tell us the integration ratio. So it's going to make it a little bit more difficult. And that'll get you a mark for that. Now we're going to be on to, I presume, the final part of the question. Deduce the structure of Z. So now what we got to do is we've got to put it all together based on the information we were looking at. So let's do that. And it's only 1 mark. So like I always say with HNMR, if you learn how to interpret splitting patterns and integration trace and use the chemical shift table, you can get most of the marks without being able to do the hardest bit, which is put the structure together. But let's give it a go. So let's remember right at the start, the first thing we did at the start of this question was we looked at 410. We looked at the hydrogen that gave us a chemical shift of 410. And remember, it had an integration trace of 2. So that told us there were 2 hydrogens. And it told us that it had a quartet splitting pattern. The one at 410 had a quartet splitting pattern. So it told us that the carbon next door had 3 hydrogens attached. Beautiful. And then we know that this was 1.26. And this told us, confirmed our stuff. It basically gave us a triplet splitting pattern, which means the carbon next door's got 2. The 126 had an integration trace of 3, telling us there's 3 hydrogens. So it's absolutely beautiful. We got all of that correct. Now, when we looked at the 410 ppm, this thing here, it also told us that we were looking at an ester linkage. It told us we were looking at an ester linkage. And so if we got an ester link, we know that's the next part of the situation. Now, for 5.5, I'm not going to zing back on the paper because it's caused me issues. For 5.5, we were looking at the hydrogen in the table that gave us a 2.19. If you look up on your chemical table now, the 2.19 also told us that it was attached to a carbonyl. So this said, oh, I'm attached to a carbonyl bond. So there we go. That's what we got from the 2.19. It had an integration trace of 3, telling us there were 3 hydrogens. So we're dealing with a methyl group. And the 2.19 told us it's attached to a carbonyl. And it had a singlet splitting pattern. The singlet means there's no hydrogens next door. Now, I might say, oh, is that R there, all of this? And is this carbonyl this? But that wouldn't make sense because the formula we were dealing with here was H7, H12, O3, and they gave us that at the start of the question. And so if I put a CH3 on the end here, that is not really going to work. I'm not going to have enough carbons and I'm missing an oxygen. So what I'm going to do, this is likely to be the opposite end of the molecule. Let's have a little look. So just to show you this here, this is going to be the opposite end of the molecule. So this is what gave us the 2.19 shift. Remember, anything around the 2.19 is telling us it's attached to a carbonyl. And so that's the opposite end of the molecule. Now we have to look at the remaining 2 shifts. We've got a 2.56 and we got a 2.60. And let's very quickly zing back up to the table. So you can see here, I've got 2.60 and 2.56. Both have got triplets. Both have got integration ratios of 2, and their ppm is basically identical. And so we'll look at what their ppm is. Just remember they've got an I integration value or ratio of 2, and they're triplets. Let's come back down. Get a little bit of space going on. Okay, so what we're going to look at here, I've obviously got another carbon, and let's just say this is the 2.56. Let's see what 2.56 is telling us. We're going to go to the table. 2.56, look here, I've highlighted that in blue. The 2.56 and 2.60 are both attached to carbonyls. So let's go back. So what that's going to tell me is, look, it is attached to a carbonyl. Look what's next door. Remember, it had an integration value of 2. So that tells me there are 2 hydrogens attached. And it had, the 2.56 had a splitting pattern. Oh my days. It had a splitting pattern that was a triplet. What does a triplet tell you? Remember the n+1 rule? Tells me that it's next door to a carbon that also has 2 hydrogens attached. Right? So that splitting pattern tells us about this neighboring carbon. And that all makes sense. Now, if I say this is the 260 hydrogen, again, it says it's connected to a carbonyl. That makes sense. Look, there's a carbonyl group there. So that makes perfect sense. And it had an I2, an integration value or ratio of 2, 2 hydrogens in its environment. And it also gave a triplet splitting pattern. It gave us a triplet split. And what does the triplet split say? Hey, it says the carbon next door has 2 hydrogens. And of course it does. Both are giving triplets because they're next door to each other and each of them has 2 hydrogens. So that is our final structure. Now, as I say, that's not easy to do, but you're going to score all the marks by interpreting the integration value or ratio and the splitting patterns and explaining what they tell you. That's how you can get all the marks. All right, people, remember sharing's caring. Help out our little poor science teacher. Hit the like, punch the bell, subscribe. Let's get to the marks. And you can see here we've got 4 compounds, J, K, L, and M, with different functional groups. We've got the skeletal formulas, and this is the student's method for identifying these compounds. Separate tubes, containing samples of each liquid, add potassium dichromate solution and warm gently. Test 2, add failing solution and cool in ice water. And test 3, add sodium hydrogen carbonate solution and test any gas produced with a lighted splint. Test 4, add bromine water and shake at room temperature. Identify the missing reagent in test 1. So when you use potassium dichromate, it's got to be acidified potassium dichromate solution. And so you just need to name an acid. It can be dilute or concentrated. They'll give you the mark in this answer, but you can name any acid you can think of. So sulfuric acid, probably the most common one in organic chemistry. You've also got phosphoric acid or hydrochloric acid, your choice. Any one of these will get you the mark. Okay, let's move on to the next part of the question. Don't forget to hit the like. It really helps me and encourages me to make more videos to help you through your A-levels. So 6.2, in addition to the missing reagent in test 1, remember we were missing the acid, there's a mistake in the method for the 2 other tests. State the 2 mistakes. So let's look at test 2, 3, and see if there's a mistake. Add failing solution in cool ice water. Failing solution is like Benedict's, you might remember from GCSE. You need to heat it, okay? You shouldn't be using iced water. And then in this last test, test 3, they've used sodium hydrogen carbonate, which releases carbon dioxide with an acid. You wouldn't be testing with a lighted splint. A lighted splint is the test, the squeaky pop test for hydrogen. Do you remember the test for carbon dioxide? It turns lime water cloudy. So the mistake 1, they used ice water with failing solution. You're supposed to warm in a water bath, gently heat it. Mistake 2, they tested with a lighted splint, which is a test for hydrogen, not carbon dioxide. The test they should have done is to pass the gas through lime water. If it turns cloudy, you've identified carbon dioxide. And this will get you 2 marks for pointing out these other 2 mistakes. Okay, 6.3. The missing reagent is added and the mistakes are corrected. Identify the liquids J, K, L, and M that would react in each test. State the expected observation for each reaction. So what liquid that reacts in test 1? So which one of these 4 liquids will react with potassium dichromate solution? Okay, so liquid J is a secondary alcohol. It's got a hydroxide group there that can be further oxidized to a ketone by potassium dichromate. So if you warm J with acidified potassium dichromate using dilute sulfuric acid, you're going to get a positive result, which will be that it will go from orange to green. Now, if we look here, we can see L is a tertiary alcohol, so that's not going to work, as tertiary alcohols can't be oxidized. But M is an aldehyde. You see that aldehyde group at the end, and it can be oxidized here to a carboxylic acid by potassium dichromate, so it will also turn from orange to green. So the answer for test 1 is that J and M will give a positive result, and the positive result is orange to green. So let's type that in. Don't forget, J was a secondary alcohol oxidized to a ketone, goes orange to green. And when we oxidized M, the aldehyde, it also went orange to green, the potassium dichromate solution. Now let's check out the liquids that would react with test 2 and the expected observation. So what is test 2? Test 2 was the potassium, have a look, add failing solution and cool in ice water. This is the correct test, so it'll be warmed in a water bath. So what are we going to find with failings? Now, failing solution tests for aldehydes. So we don't have an aldehyde in J, we don't have an aldehyde in K, and we don't have an aldehyde in L. M has an aldehyde, so we're going to get a positive result. And failing solution is like Benedict's from GCSE when you test for glucose. It's blue and it forms a red precipitate with aldehydes as it oxidizes the aldehyde to a carboxylic acid. So let's write. Okay, guys, if you're watching this, please take your time to hit the like, okay, and subscribe to the channel. The like is so important. It helps my videos get out there and motivates me to make more of these for A-level chemistry. All right, thanks for that. Now, the third test was to add sodium hydrogen carbonate solution and test any gas produced. Now, we corrected that from lighted splint to using lime water. It detects the carbon dioxide and goes cloudy. When you mix sodium hydrogen carbonate with a carboxylic acid or any acid, you're going to get carbon dioxide release. So the only 2 carboxylic acids up here are J and L. So we just need to write that in. So the liquids that react with sodium hydrogen carbonate are going to be J and L. They're going to turn lime water cloudy, and that's because they release carbon dioxide when you get those acid carbonate reactions. All right, we're now moving on to the 4th test. Add bromine water and shake at room temperature. So hopefully you remember that bromine from your basic alkanes and alkenes, bromine water is an orange solution and it tests for alkenes. It tests for that double bond. The Br2 adds across the double bond in electrophilic addition. And so we're looking for any double bonds on their own there. And there's only one with a double bond, and that's K. K had a double bond. So our expected observation is that it will go from orange to colorless. And this is nice, easy marks. So you just need to memorize these tests. And these are great for revision cards. A lot of organic chemistry is really suited to revision card techniques. All right, let's move on to the next question, which is 6.4. Figure 10 shows the apparatus that's used to separate a mixture of liquids K and M using fractional distillation. Suggest labels that should be added to positions S, T, and U. So here we've got a big condenser, we've got some beads in a column, and we've got a thermometer. So what do you think S can be? Well, S is the overall column there. What do we call that column? It's a fractionating column. You can talk about the beads that are in the column because you might think that it's labeling the beads in the column, so you can say that as well. But this is a fractionating column. They're doing fractional distillation here rather than simple distillation. The thermometer and the beads are normally a giveaway that it's not simple distillation. Now, at T, we have water going out. And at U, we have water going in. This ensures that the condenser completely fills with water and is the most efficient way of heat transfer. Okay, and make sure that all of our liquid condenses. Now, for the final bit, it says explanation. What's the explanation to why fractional distillation was used instead of just simple distillation? Simple distillation, you just boil it and you evaporate. But when we look closely at these two molecules, where are they? K and M. Let me just rub this out. We'll be able to see that their MRs are similar. Look, I've drawn out the displayed formula of K, and its molecular formula is C5H8O, which gives it an MR of 74. Let's check out the MR of M. Okay, M has a slightly smaller MR. M is an aldehyde. It's got a molecular formula of C4H8O. I've put the displayed formula here as well, and it only has an MR of 62, but it's only 12 less. They're actually very similar MRs. So here's the problem. If you were doing simple distillation and you're just boiling it up to, like, say, 75 degrees, then both are going to condense at the same time and you're going to get a mixture. So with using fractional distillation, we look at the fact that they have similar boiling points, and then we hold it exactly. We would take off the first one at 62 degrees and hold it exactly at 62, and then we'd take off the second one by boiling it above 74 once all of the substance at 62 had come off. So it's the fact that they have similar MRs and similar boiling points that means we need to use fractional distillation. Okay, don't forget, sharing's caring, subscribe, hit the like, punch up the bell. Let's get to the marks. A gas syringe that does not have any graduations is calibrated using a known mass of propanone, boiling point 56.2 degrees. The sealed gas syringe contains 0.146 grams of propanone, MR58, at a temp of 95 degree and a pressure of 103 kPa. Calculate the volume in centimeter cubed of propanone in the gas syringe. The gas constant is 8.31. Once again, I recommend when you're tackling papers, underline, highlight, and maybe even identify what you've underlined and highlighted, especially if it's a calculation question. Most important thing, of course, is to know what you're calculating. I've circled it here in blue. You're calculating volume. You'll be given R, 8.31. You'll be given temp and pressure, so you should all come to the same conclusion. You need PV equals nRT. Now, we want to find the volume, the V here. And you should recognize if we want to find V, we've got to rearrange. So I need to bring the pressure under nRT, divide both sides by pressure, and that will leave the V on its little lonesome over here. Okay, so we need nRT over P. So now all you have to do in these ideal gas equations is work out what's what, and make sure you do the conversions. So first of all, I want to work out the moles, which is N. And guess what? They're giving us mass and MR. I've just highlighted those there. And so you need to know this equation, most important one in chemistry, mass over MR times N. Easy peasy, lemon squeezy. 0.146 grams over 58. Now, what does that equal? Well, it equals 2.5 times 10 to the minus 3. It's actually 2.50 something or other. You should leave it all in your calculator in A-level chemistry. Let the scientific calculator do the work. I can't be bothered to write out really long numbers, so I'm going to round as I go, but bear that in mind, okay? The next thing we want to do is work out, we know that R is 8.31, so we really need to work out the temperature next. We don't have to work out R, it's already given to us. And the temperature for this equation, the ideal gas equation, is always in Kelvin. So add 273 to 95 and you'll get 368. Just a bit mental maths. Now, the next part that we need to work out is the pressure. Now, the pressure is 103 kPa. And what you do have to know is that pressure needs to be converted into pascals. So you need to times that by 1,000 and you'll get 103,000 pascals. You need to know about these conversions for the ideal gas equations. And then this is easy, easy, easy marks. But you have to, for A-level chemistry, know when you get to ideal gas, you're going to need conversions. Okay, so now let's plug all the figures in. So we want 2.5 times 10 to the minus 3, or whatever it is in your scientific calculator, times 8.31 times 368. Oops, I typed the wrong thing there. Let me just change that. So that should be 368, not 2.5 times 10 to the minus 3. I'll just go back and change that. We're going to divide that by the pressure of 103,000. And remember, that's going to give us our volume in meters cubed, okay? So let me just change that, because I made a bit of a mess up there by putting 2.5 times 10 to the minus 3 twice. That should be 368 there. Whack that in the calculator, and you should get 7.4 times 10 to the minus 5. There or thereabouts. And that's going to score you another mark for that. Now, that's not really our final answer. So that's our third mark. Where's the fourth mark come from? Well, this is in meters cubed. And of course, they want the answer in centimeter cubed. To turn meter cubed into centimeter cubed, we times by 1 times 10 to the 6, or by a million. Now you might say, why by a million? There's only 100 centimeters in a meter. Well, it's a cube, so 100 by volume 100 by 100 by 100 to the power of 3. So that's where you get it from. That's where you get the milli from. Okay, now in my calculator it came out as 74.2, but I'm putting 74 centimeters. If you use the rounded numbers throughout, if you don't, you get slightly higher. Now there'll be some leeway in the mark scheme for that. All right, let's zing, 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 zing down to the next question. Okay, 7.2. The gas syringe then cooled to 75 degrees without changing the pressure. Calculate the decrease in volume. If you were unable to calculate the volume in question 7.1, you should use the volume 89 centimeter cubed. That is not the correct answer. So we know that the temperature went from 95 to 75. So that's 368 to 348. And all we need to do is plug all these numbers back in the calculation and rework it out. So 2.5 times 10 to the minus 3 times 8.31 times 348K. We got the 348K because we did 95 from the original question, take away 75, which the temperature was lowered to, divided by 103,000. It told us the pressure was the same, 103,000. And we're going to get, bada bada bing, bada bam, bada bong, we're going to get 7 times 10 to the minus 5. There or thereabouts, 70169 or whatever. But 7 times 10 to the minus 5. Now, once again, I need to times by 1 times 10 to the 6, not 1 times 10 to the minus 6. Oops. I nearly wrote, 1 times, not minus 6, 1 times 10 to the 6. And that's going to give us like 70 centimeter cubed. But of course, I nearly wrote that answer in. That's not your final answer. That's only 1 mark, all that work. It said the decrease in volume, which I've just circled here. So 74 from the original volume in the original question minus 70 times 70 centimeter cubed equals 4 centimeter cubed. Now, there we go. Let's move on. About time.
Keep moving on, keep moving on, keep moving on, keep moving.
7.3, we've been given the total uncertainty, which is plus or minus 0.001. And that's the uncertainty in the balance we used to measure the mass in the first question. It now says what will be the uncertainty in the volume. Well, we need to start off with our uncertainty in the mass. And how you do that is you do the uncertainty over the mass, over your measurement. So 0.001 divided by 0.146 times 100, we're going to get 0.685. Now, that's a percent. Don't think that means 68%. Okay, so that scores us 1 mark. But we've got another bit to this, which is probably the bit that some people might mess up on. So our original volume was 74 centimeter cubed from 7.1 from the first question. That's the volume we calculated. Of course, you can use 89 centimeter cubed if you messed it up. So now we want to work out what the uncertainty is in that. So this 74 centimeters is possibly going to be 0.685 out, is how much it's going to be out as a percentage. So what I need to do is 0.685 divided by 100 times 74 centimeters, because, yeah, and that'll get you the correct answer. Remember, when you times by a percentage, you need to turn it into a decimal of that percentage. So you've got to divide by 100. So you just got to remember to divide the 0.685 by 100. Otherwise, you're doing 68.5% times the volume. And so it's like 0.51, but I'd probably call it zero point 0.5 is a better answer to put down for the centimeter cubed uncertainty. And that's the end of 7.3. Let's zing on to 7.4. We're getting there, folks. Last part to this question. Let's go. 600 centimeter cubed of propanone is mixed with 2,800 of oxygen in a container at 60 degrees and 100 kilopascals. The mixture is ignited. When the reaction is complete, the remaining mixture of gases is cooled back to 60 degrees at the same pressure of 100 kilopascals. And we have an equation here, which means we're going to use coefficients. So we got 600 centimeter cubes of propanone, and we got 2,800 centimeter cubed of oxygen. We don't know which one's in excess yet. The pressure's the same before and after. Now that's interesting, because if the pressure is the same, we could just, it means our centimeters are like equivalent to moles, basically. So what we're going to do here is we're going to use the ratio of the coefficients. So propanone to oxygen is 1:4. So for 600 centimeters of propanone, I'm going to need 2,400 centimeter cubed of oxygen, right? So it means I'm going to need 2,400 centimeter cubed of oxygen to react with that 600 centimeter cubed of propanone. So the leftover oxygen is going to be 2,800 minus 2,400 centimeter cubed, which is the amount of oxygen that reacts fully with the propanone and uses all the 600 propanone up. And it means I'm left with 400 centimeter cubed of oxygen left over. And that's a gas. So that's going to be part of our remaining mixture of gases that they're asking us to find the volume for. We don't need to take account of the water because that's a liquid, so it's not relevant. It's not going to be part of the volume of the gases, but we do need to work out how much CO2 is produced. Now, because we've got 600 propanone and the ratio of propanone to CO2 is 1:3, we're going to times the propanone by 3 to get 1,800 centimeter cubed of carbon dioxide. Remember, the propanone is the limiting factor here, so that's the max CO2 we can make. We need to whack the leftover oxygen and propanone together, 400 plus 1,800, and that means we've got 2,200 centimeter cubed in our mixture of gases left over. Okay, going through a chemistry A-level question here. Let's get into it. This question is about biofuels. Palmitic acid can be made by hydrolysis of the triester in palm oil under acidic conditions. Palmitic acid can be used as a biofuel. Complete the equation for the hydrolysis of the triester in palm oil under acidic conditions. So here is our triester. We've got acidic conditions, you see by the hydrogen ions there on the arrow, and we've got 3 water molecules. So we're really looking at hydrolysis of this bond. You're just looking to hydrolyze this ester bond and show the products. And of course, for those biologists, you know the product is going to be a glycerol molecule, propan 1,2,3 triol, IUPAC name, and it's going to be hydrolyzed here. So the first question literally says complete the equation. So they just want us to write the products out. So what are going to be the products? Well, first of all, we're going to make a molecule of glycerol. So we're just going to write the formula like this: CH2, which is the first bit there. You're going to attach an OH there. So you put in brackets the OH to show it's attached to this carbon and not to the carbon after it. Then we've got CHOH. Again, the brackets show which carbon it's attached to and not the one after it. And then for the last one, we can just put CH2OH, and we don't need brackets because there's no more atoms following. So the OH must be attached to the carbon before it. Okay, so that's a glycerol molecule is formed. What else do you get? Well, you get 3 fatty acids. Okay, and I've just circled one of them. What you've got to do is redraw that out. You get 3 lots of palmitic acid. So you're adding the OH bond to the glycerol, but of the 3 water molecules, 3 hydrogen ions add to the COO to make the carboxylic acid group. So we're going to get CH3, CH2 with a 14, COO, and of course that would be negative, and you get that positive hydrogen ion that snapped off when the water was involved in the hydrolysis, and that hydrogen ion joins to that carboxylate group and forms a carboxylic acid. Like that, and you're going to have 3 of them. Okay, 8.2. Palmitic acid burns in air. In a calorimetry experiment, combustion of 387 milligrams of palmitic acid increases the temperature of 0.150 kilogram of water from 23.9 degrees to 37.5 degrees. Calculate in kilojoule per mole for the enthalpy of combustion of palmitic acid in this experiment. Give your answer to the appropriate number of significant figures. The specific heat capacity of water is 4.18 joule sorry, per gram. So, and we want to do this to the appropriate number of significant figures at A level, that is 3. And this is worth 5 marks. So, first up, I'm going to use this equation, Q, or you can call it E. E for energy transferred into the water is the mass of the water times the specific heat capacity times the change in temperature. Now, do note at this point that the temperature has gone up. And what does that mean? That means it's an exothermic reaction. It must be releasing heat to the environment. This is important when we get to the final calculation and the 5th mark of this question. You should pause the video at this point, get a pen and write down on scrap paper, see if you can work the answer out. Okay, let's go through it. So Q stands for energy. In this case, you can use E if you like. Equals 150 grams. Why grams? Because mass is in grams. So you need to obviously times by 1,000, 0.150, times the specific heat capacity, which is 4.18. And because the specific heat capacity is in grams, it's got G to the -1. That's why we want to do convert our mass. If the specific heat capacity was per kilogram, then we would keep it in kg. Now, we're then going to multiply that by the temperature change, and this gives us 8,522.2. 8,527.2 joules. Now, we need to turn it into kilojoules. How do we know this? Look at the unit at the bottom. I've circled it. The unit's in kilojoules. So we've got to divide by 1,000, which will give us 8.5272 kilojoules. So we're only down to like 8 kilojoules now of energy has been transferred into that 150 grams or 0.150 kilogram of water. So this will have picked us up at least 2 marks, possibly 3 at this stage. Now, the answer is kilojoule to the mole to the -1, which means kilojoules divided by moles. So I need to do 8.5272 and divide it by the moles. Now, how do I work out the moles? You know the triangle, mass over mR equals moles. So the mass is 387 milligrams. We need it in grams. Mass is in grams in chemistry. So we're going to do 0.387 because we're going to divide by 1,000 to turn into grams. So 0.387 grams over the mR of palmitic acid. So at this point, you'd have definitely secured 3 marks, but it's quite difficult now. You've got to look at the formula of palmitic acid. See up here, it's CH3, CH2, 14, COOH. You've got to work that out yourself, and it doesn't really give you too much of a hint there, other than the fact that you've been given the mass of palmitic acid. You should work out, I need the moles because my answer is per mole. So you're going to need to work out the MR. So how do we work out the MR of palmitic acid? Well, what I'm going to need to do is go, well, CH3, that's about 15, 12 for the carbon, 3 for the hydrogens. Then I've got 14 for CH2, 2 hydrogen, 12 for the carbon. I've got times that by 14, so 14 times 14. And then I need COOH, so that's 12 plus 32 for the 2 O's, and another one, 33 for the, another one for the hydrogen. And you're going to get a total of 256. So then do 0.387 grams, which is the mass, divided by 256, the MR, and that's going to give us 1.512 times 10 to the -3, and that's our moles. So now I just need to divide kilojoules by moles. So the hardest bit really was working out the MR of the palmitic acid. You could easily make a mistake there. So, final answer, 5641 kilojoule per mole to the -1, but I've just spotted it's 3 significant figures, isn't it? So at A level, we go to 3SF if they ask you for significant figures. So it needs to be 5640. You're only allowed to give 3 numbers that aren't a 0. So, something else I forgot. We need a minus sign. This is exothermic. Remember I pointed out at the start the temperature went up. So you have to have a negative sign with your answer. Okay, moving on, 8.3, state how the value calculated in 8.2 is likely to differ from the data book values. Give one reason other than heat loss for this difference. So of course our value is going to be less exothermic. It's lost a lot of heat. When you do calorimetry, you always lose heat through the equipment, through the air, to the surroundings, so you get a less exothermic value. The temperature doesn't go up as much as you think. But we need to give another reason why the temperature doesn't go up as much as you think. And this could be down to something called incomplete combustion. And incomplete combustion releases less energy than when you do complete combustion of a fuel. And so our answer here is incomplete combustion. Superbulous. Okay, let's move on to the next question. Now we have this next one is 8.4. A sample of a different biofuel made from sewage sludge is found to contain 37.08 carbon, 5.15 hydrogen, 24.72 oxygen by mass. The rest of the sample is sulfur. Calculate the empirical little bill. So we're going to go for carbon. We want to do 37.08. We're going to divide that by 12. And then for hydrogen, we want to do 5.15. We're going to divide that by 1. For oxygen, we want to do 24.72. We want to divide that by 16. And then the rest of the sample is sulfur. So in order to work out the sulfur, I need to do 100 minus 37.08 plus 5.15 plus 24.72. And that's going to work out what sulfur is, and it works out at 33.05. And I'm going to divide that by 32. So if you carry this out, you're going to get the first mark. And we're going to get 3.09. We're going to get 5.15, 1.545, and 1.0328, something along those lines. So now I want to divide all by the smallest. Divide all by the smallest. So we want to ratio them. So, and then my answers here, I'm going to do in another color. This is all getting a bit confusing. So this is going to be 3, 5, 1.5, and 1. 3, 5, 1.51. So what I need to do is now multiply to get whole numbers. So I'm going to multiply. Yes, we must multiply. And then we're going to get carbon 6, hydrogen 10, oxygen 3, and sulfur 2. And that is going to get us our, whoops, kind of getting a bit bent there. That's going to get us our 3 marks. Okay, beautiful. Now let's zing off of this. Scroll down, we're on 8.5. Okay, 8.5. Complete combustion of biofuels made from sewage sludge produces greenhouse gas carbon dioxide. Name one other possible environmental problem with the complete combustion of this biofuel. State the formula of the pollutant responsible for this problem. 2 marks. So we were told that it had sulfur. And of course, the environmental problem is acid rain caused when SO2 dissolves in H2O or reacts. Sod it up, but dissolves. The main thing is acid rain. It actually reacts. It's a reaction rather than a physical process. So I probably lose myself a mark there. But acid rain, and the formula is SO2, which is formed when sulfur atoms are combusted in O2. S plus O2 goes to SO2. All right, I'm being a bit extra. The only thing you needed to put here was sulfur dioxide. Okay, 2 marks. Beautiful. Right, let's move on. Wasting time. Wasting your time. Right, 3 marks. Holy shamoly. It's a lot of work for 3 marks. So let's have a little butcher's book. So what we're going to do here, holy, right. Ethanol is a biofuel, can be produced by the fermentation of glucose. Glucose is the structural formula shown. Boom, bam. Um, Shows some mean bond and enthalpy values. Boom, boom, boom. Use the equation and the data in table 3 to calculate an approximate value for the enthalpy of fermentation of glucose. For this calculation, you just assume that all the substances are in the gaseous state. 3 marks. Okay, me, myself, and I, baby, me, myself, and I. I find this difficult, so I'm going to draw the displayed formula of glucose, which is a bum. If you're very spatially aware, you don't need to do this, but I am not going to claim that I am spatially aware. I failed my driving test 3 times, so my spatial awareness is bad. Let's go here, peeps. What we're going to do is zing that there, zing that there. Oh my gosh. I've got issues. Right. Okay, that's a glucose molecule. We need to add up, first of all, how many CH bonds are there? So I've got 1, 2, 3, 4, 5, 6. Hold on. 1, 2, 3, 4, 5, 6. Why have I got 7? I'm missing something. Why do I get 1, 2, 3, 4, 5, 6? Ah, right. So there's 1, 2, 3, 4, 5, 6, 7. So first of all, 7 times 4, 12. Okay. And then what we're going to do, go next to the 3, 4, 8s, and you see you've got 1 there, 2 there, 3 there, 4 there, 5 there. So we're going to go 5 times 3, 4, 8. And then the next thing I want to do is the CO bond. And I've got 1 there, 2 there, 3 there, 4 there, 5 there, 6 there, 7 there. So 7 times 3, 60. And then, no, we've got nothing there for the CO bond. We've got the OH bond there. We've got 1, 2, 3, 4, 5. So 5 times 4, 6, 3. And this is going to give us a total of 9, 4, 5, 9. And that is our bond breaking. And we want to minus our bond making. So now we need to work out the bond making. Um, so I'm going to go over here and draw out ethanol. So we've got 2 of them. So I'm going to do 2 times all of this. So 1, 2, 3, 4, 5. So I've got 10 times 4, 1, 2. Then I have 1 cc, but 2 times. So I have 2 times 3, 4, 8. I have 1 times, so 2 times 3, 6, 0. And then 1 OH, but 2 times. So 2 times COH, 463. 463. Whack that all together in a calc. That equals 6462. Hold on, we're not finished yet for bond making. Bond making, I've got 2 times this, so carbon dioxide looks like that, but I've got 2 times, so I want 4 times 805, and I want to add that to that, okay? And if we whack those together, we're going to get 9682. So 9459 minus 9682, and that is going to give me minus 223 kilojoule per mole minus 1. And your marks, you're going to get a mark for that, you're going to get a mark for that, and you're going to get a mark for that. 8.7, the carbon dioxide produced from fermentation can be reacted with steam to make more ethanol. The equation for this is blah, 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 blah. Shows some standard enthalpies of formation. Now, what they've given us here is standard enthalpies of formation. This immediately tells me it's Hess's law. We've got to calculate the enthalpy change. Booyaka Shan. So what I'm going to do here, guys, is I'm going to write this out. 2CO2 plus 3H2O. I'm going to smash that over there to make C2H5 OH plus 3O2. Now, this is just my way of doing it. You don't have to do it like this. But the moment I see that this is formation, I draw two arrows going up, one to the reactants, one to the product. So I draw one up to the reactants, one up to the product, and then I look at what elements there are. And you don't really have to do this because unless they ask you to set it out, formation is from the elements in their standard form. So there we go. I'm not going to balance it all up. There's no need. I need 2 carbon dioxide. So I'm going to go 2 times minus 394. There's a reason these arrows are key for me. Some people do this in their head and they don't need them. And then I've got H2O and I've got 3. So I'm going to be 3 times minus 242. And then over on this side, oxygen is zeros in its elemental form. We don't worry about that. But the ethanol is minus 235. Now, what I'm going to do is add all of this together. This makes minus 1514. And over here, that is just that. So that is minus 154. Now, what I do, for Hess's law, I draw a big arrow that goes round like that. And I keep things, if the arrow that I've drawn round from left to right is in alignment with my formation arrow, I keep that number the same. If they clash like this, I'm going to reverse this number here. So this becomes plus 1514 minus 235. And I'm going to get plus 1279. Welcome to Let's Get to the Marks. This is question 9 of the 2023 paper 2 for AQA chemistry. The question is about ethanoic anhydride. In the gas phase, ethanoic anhydride CH3CO2O decomposes to form ethanone. The equation is CH3CO2O goes to ethanone and ethanoic acid. Ethanone is the simplest member of the ketene homologous series. Ketenes all contain one carbon-carbon double bond and one carbonyl bond. So it's got a CC bond and an O, so I'm going to draw out ethene here. It wants us to deduce the general formula for the ketene homologous series. So I've written out the displayed formula and the molecular formula because it's easier than looking at the structural. But you won't really be able to work out the general formula unless you write out a couple of members of the homologous series. So based on the fact they need to have a carbonyl group and a double bond, we can kind of work out their molecular formula. So propanone or propene-1-one would be C3H4O. And let's have a go at doing butanone too. So that is going to be CH3, CH2, CHCO, well, with a double bond and the carbonyl group. And then write out that molecular formula and now try to create a general formula that will apply to all 3 of these formulas, molecular formulas. And so you're really looking at N. N is the number of carbon atoms. So, you know, for alkanes, you have CN H2N plus 2, or for alkenes, you have CnH2n. So you're really looking at N is the number of carbons, and then work out your hydrogens from that. So if we look at this first one, we can do, if N is 2, we can go times 2 minus 2 also equals 2. So 2 carbons, 2 hydrogens. On this second one, this propanone or propan-1-one, we can have, when N is 3, we would go times 2 is 6, minus 2 is 4. And that works out with our formula as well. And then for the third one, when n is 4, because the carbons are 4, we go times 2, which is 8, minus 2 equals 6, and that works out with our C4H6O formula. So we can now construct the general formula, Cn H2n minus 2 O. All of them have one thing in common, they all have one oxygen atom. And remember, with successive members of a homologous series, they go up by 1 carbon and 2 hydrogens, as you can see from those first 3 I did. Right, let's look at 9.2. Make sure you hit the like, please. 9.2. Figure 11 shows an incomplete suggestive mechanism for the decomposition of ethanoic anhydride. Complete the mechanism in figure 11 by adding 3 curly arrows and any relevant lone pairs of electrons. Okay, so what you want to do here, it says the word decomposition. So we know this is breaking this ethanoic anhydride. You've got to ask yourself where it's going to break. You can see from the intermediates, it's going to smash in half there because you can tell from the intermediates we've got over here. So where are the curly arrows going to go? Well, we're left with a carbocation there. And that means that some electrons are going to leave that carbon. So they're going from this bond to the oxygen. How do we know that? The oxygen on the other intermediate is negative. So it's left this positive carbon because 2 electrons have gone. And where have those 2 electrons gone? They've ended up on the oxygen, which is where I drew the curly arrow in the reactant to the intermediate. Now look, if we look at over here, the pair of electrons have gone to a hydrogen. So we're going to need to show that. First, I want to get rid of the positive charge on the carbon atom on the carbocation. So I'm showing a pair of electrons going to the positive carbon, and that's going to reform. Well, it's going to form a double bond, you see, after step 2. And then the lone pair of electrons on the negative oxygen are going to go to the hydrogen, which makes that OH group after step 2 on the bottom product. And there we go. To get the 3 marks here, you need the 3 curly arrows and the lone pair of electrons. You need 4 things to get the 3 marks. Boom, boom, boom. Okay, 9.3. This is the Arrhenius equation. So for a chemical reaction, the relationship between the rate constant K and the temperature T is shown by the Arrhenius equation. K equals AE minus EA over RT. For the decomposition of gaseous ethanoic anhydride, the activation energy is 34.5 kilojoules. And A is 1 times 10 to the 12, and K is 2.48 times 10 to the 8. Can you calculate T, essentially? Right, first of all, I want to get rid of that dirty exponential number. See the little lowercase e? So I'm going to ln each side. You'll find there's a little button with ln on your scientific calculator. You can just put the ln there, and I'm then going to divide, that will get rid of the e, by the way, and then I'm going to divide the ln k by the ln a, and I'm going to get ln k over a equals minus ea over rt. By the way, there's like 3 different ways you can rearrange this to get t, but this is just the one I do. It doesn't mean it's very good, but when I do ln k over a, I get 8 minus 8.302. Now, the activation energy should be in joules, not kilojoules, so I'm going to do minus 34,500. Over the top of 8.31, that's R, the rate constant, times T. And I'm therefore going to do 34,500 divided by 8.302. The minuses cancel out. And we're going to get 4,155 or something along those lines. Calculator. And that 4,155.6 is basically equal to 8.31 times T. So I'm just going to do 4155.6 divided by 8.31, and that's going to give me T, and that gives me 500, like 500.075 or something like that. So basically 500 is the temperature. And that's the way I did it, but there's plenty of ways to skin a cat. So let's move on to the final part of the question, and that's 9.4. So let's zing down and get on with 9.4. We pick up the marks. Here's where roughly where you get the marks, roughly. Let's zing down 9.4. Sketch the Maxwell-Boltzmann distribution of molecular energies for the gaseous ethanoic anhydride at temperature T1 and at a higher temperature T2. Include a label for each axis. Mark on the appropriate axis a typical position for the activation energy. Explain why the rate of reaction is faster at T2. So Sometimes you get 3 marks for the graph, 2 for the explanation. The way this mark scheme does it is 4 marks for the graph and the labeling and 1 mark for the explanation. Anywho, this is my first temperature, so you just draw a graph like that, like my one in blue. Now, obviously, you might not have different color pens because you're in an exam, so you can just label these with T1 and T2. My higher temperature is the one in red. I'm going to put number of particles or mean number of particles, whatever, on the side. I'm going to have energy at the bottom. So number of particles on my y-axis, energy on my x-axis, and then the graph. Now the graph, you just have to learn this off by heart. When you're doing a higher temperature, make sure the higher temperature is lower than the colder temperature. Make sure the higher temperature crosses the colder temperature, i.e. T2 is crossing T1 at just 1 point on the graph. And roughly the area underneath each graph is equal visually by the eye. So visually by the eye, the area under the red graph is roughly equal to the area under the blue graph. And that is going to get you a mark for making them roughly equal. We've not changed the number of particles here. We've just increased the temperature. So what we've done is increased the energy that some of the particles have at the higher temperature. Now, what I haven't done here is included the activation energy. So how do you represent activation energy? Well, you're going to use a dotted or dashed line towards the end of the graph. You can write AE or EA, energy of activation or activation energy, and indicate that. That's going to get you a separate mark. And the explanation, well, if you check out the area under the red line, more of the particles at T2 have energy greater than the activation energy. Therefore, more of the particles have a successful collision and reaction. You can also say as more of the particles at T2 have higher energy, there will be a higher frequency of successful collisions. They didn't include that on the mark scheme, but I've seen this exact same question on other AQA chemistry mark schemes where there were 2 marks for the explanation and you needed to say more of the particles have a higher amount of kinetic energy, so more frequent successful collisions, blah, 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 blah. That little spiel as well. On this mark scheme, it just wanted you to say a greater number of particles at T2 have energy above the activation energy. Zing, bing, bong. That's the end. Guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Don't forget, let's get to the marks. I'll see you in the next video.
You're still here? It's over.